Hey class, this is Mr. Roberts at Shasta High School, and let's take a look at our homework. Tonight we're doing questions 47 through 51. And this first question asks us to find to decide whether or not the following relationships are functions. Remember, a relationship is just a generic term for a connection between one set of numbers or things and another. And in this first instance for A, we would have to say that this relationship is not a function. If I zoom in a bit here, you can see that, for example, it looks like when A is maybe like the number 1/2, you can see that there's at least two values here, right? Two values. So this value and this value are two different outputs. So in order for this relationship to be a function, a particular x may have at most one output value. Let's look at the next one. It's a table of numbers. And as I look at it, I can see that the number -3 is always producing an output of 19. And as I look down here, I don't see -3 giving me anything else. So 3 is always producing 19 consistently and predictably. Every single time I give this function -3, it gives me 19. When I give this function 5, it's also giving me 19, but you can see 5 is always giving me a 19. So that's functioning. 19 is always producing a value of 0, and 0 is producing a value of -3. So this relationship is a function. If I wanted to break it, if I wanted this to not be a function, for example, I could say that the output 5 may give me the number 21. All of a sudden, these two, right, these two particular values would break this, and it would no longer be a function. Because I could see that I would have sometimes the number 5 would give me an output of 19, and sometimes the output or input of 5 would give me an output of 21. So that would not be a function in this case. But as it's written, this is absolutely a function. Each value of x produces at most one value of y. Let's look at this next value here. This relationship turns out to not be a function, and it's because of this value, right? It's because of the 7. So I have a 7 value here and a 7 here. This 7 is producing an output of 10, and sometimes when I give it 7, I get an output of 3. So because 7 can give me inconsistent or unpredictable values, this is not a function. If I was to change this and this was not the number 3, let's say that this was a 10 also, at this point it would be a perfectly fine function. But as it's written, again, I like that contrasting thing. As it's written, it is not a function because 7 can give me 10 or 7 can give me 3. And the last one's this. And as I look at it and I run like this, let's make it 90 degrees so it is a vertical line. As I run this line through it, you can see every single time I draw a vertical line, I can see that each vertical line is only touching my relationship once, right? It's never touching it more than once. So each and every single x that I'm identifying only gives me, like, this x only has one y. This x produces only this y. This x only produces this y. So this is a function machine, unlike A. It is consistent and predictable. It does ask me here, it says find the x and y intercepts for the graph of the relationships in problem 47. So there were two relationships here. This first one turns out to have two x-intercepts, right? It's got an x-intercept at, it looks like the x-intercepts for this one occur at -1, and they also occur at +1. So -1 is an x-intercept and +1. And the y-intercepts, there's two of them for this function, right? One of my y-intercepts is right here at -1. I'm crossing the y-axis. And the other one is at +4. So I have two x-intercepts, -1 and 1. And I have two y-intercepts, -1 and 4. For this function, I've made a mess of it. Let me erase this. So if I identify the x-intercepts, I'll do that in red. My x-intercepts occur here, here, and they occur here. And I only have the one y-intercept right here. So if I was to say the y-intercept is at -1, and the x-intercepts, where I'm crossing my x-axis, my x-intercepts are at -1, and +1. So that's the answer for the second question, 48. Let's move down to 49. 49 says, for the following tile pattern, find the growth rate of the pattern. Determine the number of tiles added each figure. So it does say that I'm supposed to sketch figure 1. Figure 1 is not given. And actually, this is figure number 4. But if I look at it, as I go from figure 2 to figure 3, I can see that these 2 tiles are added. They are new. And that looks like it's it, right? So just those 2 tiles are added. And when I go from figure 3 to figure 4, these 2 tiles are added. So it looks like what's happening is that I'm just continuing to add 2 tiles off to the right here. So if I was going to sketch figure number 1, not figure 0, but figure number 1, if I was to sketch figure 1, it would look like, what would it look like? It would look like just like that L, right? It would have these 1, 2, 3, and then it would have 1, 2, 3 down below there. So that looks like it's figure number 1. And as I move forward, figure 2 tacks on these 2 tiles. And then from 2 to 3, I tack on these 2 and these 2. So my growth rate for this is add 2. I should be careful because they tell me the figure 1, but not the 0th figure. So I don't know if I can come up with the rule necessarily. So what I'm going to do is I'm just going to say, well, look, I'll just go for a table representation. So this is going to be the figure number and the tile. Figure 1 has 1, 2, 3, 4, 5 tiles. Figure 2, 1, 2, 3, 4, 5, 6, 7, add 2. Figure 3 has 7, 8, 9. Figure 4 has 9, 10, 11. 5, 6, 7, and then the last one is going to be figure 8. 9, 11, 12, 13, 13, 14, 15, 15, 16, 17, 17, 18, 19. So all those should be up by 2. 5, 6, 7, 7, 8, 9, 10, 12, 14. Yeah. So I believe that figure 18 should have 18 tiles. And we are moving on to question number 50. So question 50 says, solve each equation below. And we're also admonished to check our solution. So when we're asked to check solution, that means we're going to take what we think is the answer, plug it into the original problem, and verify that it does indeed work. So for this one, I'm going to begin by simplifying by combining the 6 and the -3. When I do that, I'm going to get 6 minus 3 is 3, so this is going to become 3 minus x is 10. If I take away 3 from each side, I'm going to get the opposite of x is 7, and therefore x should be, if I multiply both sides by -1, x should be -7. So if I plug in -7 to this, notice it becomes 6 minus a -7, and then minus 3. Well, 6 minus -7 is going to be 14. Nope, it's not. It's 13, because that's 6 plus 7, which is 13, and 13 minus 3 is 10. So that does check. Next problem, solve for x. I'm going to take away 300 from both sides, so this equation is going to become 100x is equal to -100. That's me subtracting 300 from each side of the equation, and then I divide both sides by 100, and I get that x should be -1. If I plug in that x is -1, this becomes 100 times -1, which is -100, and yep, -100 plus 300 is indeed 200, so that does check. Let's check do number 3. I'm going to say this now. I say it a lot, but I do not particularly like problems with fractions. I think I'm going to begin by, I'm going to add 2 to both sides. And I don't know if this is really what I want to do, but I've got the 1/3 x, and if I add 2 to this side, it's going to become plus 6. And if I add 2 to the other side, it's going to become x, and then x minus 2 plus 2 is just plain old x. I don't like the fraction, so what I'm going to do is I'm going to multiply every single term by a new factor of 3. And as long as I do that, right, as long as I'm multiplying both sides, all terms on both sides by 3, I get an equivalent of fraction. So on the left-hand side, 3 times 1/3 is going to give me x. 6 times 3 is going to give me plus 18. And then 3 times x is going to give me 3x. So I have x plus 18 equals 3x. And again, what did I do? I multiplied each term by 3. This got multiplied by 3 times 3 and times 3. So multiplying all of the terms on both sides by the same value gives you an equivalent equation. Next, I'll take away 2x from both sides. So 18 is, or I'm taking away a single x. 3x minus that x is going to be 2x. And when I divide both sides by 2, I get 9. Should be what x is. X should be the number 9. And then as a quick check, 1/3 of 9 is 3, so this becomes 3 plus 4 on the one side. And on the other side, it's 9 minus 2, right? 9 minus 2. 3 plus 4 is 7, 9 minus 2 is 7. Yep. When x is 9, it makes both sides equal to the same thing. It makes both sides equal to 7. And the last problem is this one. I'm going to add 2x to each side. So this is going to become, oops, not 2. It's going to become 36. And I'm adding 2x to that side. So that's now, there's no x's there. When I add 2x's to the other side, it's going to become just a single x plus 2. And if I take away 2 from both sides, I get that 34 should be what x is. X is 34. If I check that, yikes. All of a sudden I'm like, okay, you're all talk, but you want a calculator, don't you? Yes, I do. Let me grab a calculator here. So with a calculator, I could say 36 minus 2 times, and I'm minus 2 times 34. When I do that, I get negative 32. So when I plug positive 34 into this side, it's giving me a negative 32. And on the other side, right, the other side's got this, whatever x is the opposite of x, it says the opposite of x and then plus 2. So I'm going to go the opposite of x, x is 34. So I've got the opposite of 34 and then add 2 to that. And I can see when I do that, oh, it makes that side also 32. So both sides end up becoming the number 32. Or negative 32, so I can see, yeah, when x is negative 32, both sides are the same. And then the last question I have here, it says, hey, the diagram at right shows a flat surface containing a line and a circle with no points in common. Visualize moving the line and or the circle so that they intersect at exactly 1 point, 2 points, or 3 points. Decide if each of these situations is possible, and then illustrate the ones that are with examples. So again, here's my circle and line, and I can take, I think this is nice. I can take this, and if I draw a rough circle, it turns it into a nice circle. That's very nice. Oh, I don't need the calculator. Turns it into a nice circle. So there's a nice circle. I don't need to type anything. And if I move this line down, I can see, if I move it just a little bit, I can see that it gets to where it will touch that circle at exactly a single point. So touching the circle once is definitely possible. If I take that circle again, and if I, whoops, that's now a crazy looking oval, Mr. Roberts. Let's try a circle, a circle, a circle, a perfect circle, close enough. And if I draw that line down again, now you can see I've got this line drawn so that it's touching in 1, 2 points. And I can do this in a lot of ways, right? You can see there, a line would touch twice. This line would touch the circle twice. But no matter how often I try, I don't think it's possible for me to get the line to touch the circle more than twice. So I'm going to say that with the circle and the line, I can have it intersect once, or I can have it intersect twice, but not more than that. All right, guys. This is Mr. Roberts. I have a great day, and I look forward to seeing you again soon. Talk to you later.